In these questions, we're just looking at first order reactions. This question's about the fictional decomposition of Ra2, which we can see in our chemical equation there. We're told that the scientist experimentally determines the differential rate law and gets rate is equal to K multiplied by the concentration of Ra2. So that is a first order equation as expected. We're also given the rate constant K. Our first step is to find the half-life of the reaction. Let's head to our reference sheet and see what we can find. So here's our equation for half-life. T half is equal to 0.693 divided by K. Let's write that down. T half is equal to 0.693 divided by K. And what the half-life means is the time taken for the concentration to halve in a reaction. So if you imagine, I'll do a little graph showing a first order reaction. This is what our concentration over time would look like. And we start with a certain concentration, and at some point the concentration has fallen to half of that amount. So the time taken to fall to half that amount, that would be our half-life. And it's going to be the same again. If we fall to half again, you can see it takes the same length of time. If we fall to half of that amount, it takes the same length of time, and so on and so on. So that's the idea of half-life. To calculate the half-life, if we know the rate constant, we can put them into this equation. So we can do that now. Our half-life is going to be equal to 0.693 divided by our rate constant K, which is 0.0347. If we put that into our calculator, we get a half-life of 20.0 seconds. So let's fill that in here. So we're then told we have an initial concentration of Ra2 of 6 molar, and the experiment proceeds for 140 seconds. So our first step is to figure out how many half-lives have passed. So let's draw a little table to help us. We've got concentration of Ra2, and we've got the time that has passed. So we know that we start with a concentration of 6 molar at a time of 0 seconds. Now we know that after 20 seconds has passed, because that's the half-life, our concentration will have halved. So then our concentration will be 3. So that's after 20 seconds. We need to figure out what happens after 140 seconds. So let's go by another half-life. After another half-life passed, we're at 40 seconds. Our concentration will have halved again. So it'll be 1.5 now. After another 20 seconds, our time is 60 seconds. Our concentration halves again. Now we have 0.75 molar. After another 20 seconds, our time is 80 seconds, and our concentration is now 0.375, because that's half of 0.75. 20 more seconds later, our time is 100, and our concentration has halved again, getting us 0.188 as our concentration. 20 more seconds later, it's halved again, and our concentration is now 0.0938. Finally, we have one more half-life to get us to 140. And at that point, our concentration halves again. It's 0.0469. Okay, so we halved once, twice, 3 times, 4 times, 5 times, 6 times, 7 times. 1, 2, 3, 4, 5, 6, 7. We've had 7 half-lives pass to get to 140 seconds and a concentration of 0.0469 molar. So let's fill in our answers over here. How many half-lives have passed in 140 seconds? The answer is 7 half-lives. And what is the concentration after 140 seconds? it's 0.0469 molar. Now, we did it using this table method. There's a quicker way to do it if you'd like. So the other method, we know that the total time is 140 seconds. We want to know how many half-lives have passed. Well, we know our half-life is 20 seconds. So if we divide that by our half-life, 140 divided by 20 is 7. So that gets us 7 half-lives. So we know 7 half-lives have passed in 140 seconds. Then to find the final concentration, instead of doing the table method, which works just fine, what we can do is take our initial concentration, which is 6 molar, and we can multiply it by half, and then we multiply it by half again and again and again 7 times, which is the same as multiplying by half to the power of 7. So that's the number of half-lives there. If we put that on our calculator, we get exactly the same thing. We get 0.469. So this is a kind of shortcut method. Instead of using the table, you divide the time taken by the half-life to get the number of half-lives. Then you multiply your initial concentration by a half to the power of the number of half-lives to get your final concentration. Let's do one more question of this type. In this question, a fictional scientist is carrying out the fictional decomposition of XL2, which we can see in our reaction there. The scientist experimentally determines that the differential rate law for this reaction is rate equals K multiplied by the concentration of XL2. That makes sense because it's a first order reaction. We're also given this graph. It says the scientist carries out an experiment to continuously measure how the concentration of XL2 varies over time as the reaction progresses. So there's our concentration of XL2 on the y-axis and our time on the x-axis. The first question is asking us, what is the half-life of this reaction? So on our graph, we can see how our concentration has changed over time. We can see it started at 16. And remember, the half-life is the time taken for the concentration to halve. So 16 divided by 2 is 8. So by the time our concentration reaches 8, 1 half-life will have passed. So let's see on our graph, that would happen at 50 seconds. So that means our half-life is 50 seconds. Let's just test that in our answer box over here. Awesome. So now I just want to show you how the half-life can be measured at any point on the graph and it's going to be the same. So for example, we could start at 8 this time, divide 8 by 2, that gets us 4. So between 8 and 4, we should have 1 half-life pass again. That gets us to 100. So between 8 and 4, we've gone from 50 seconds to 100 seconds. That's 50 seconds that have passed again, so that makes sense. Let's try it with 12. Let's say we started with 12. 12 divided by 2 is 6. So to get from 12 to 6, we should see a half-life pass. So here's 12. Here's 6. That goes from 20 to 70, which is 50 seconds again. So it doesn't matter where you measure it on the graph, your half-life is always going to be the same. Okay, our next step is finding the rate constant K for this reaction. So let's head to our reference sheet. And down here we can see the equation for half-life. Half-life is equal to 0.693 divided by K, which is the rate constant. So T half is equal to 0.693 divided by K. We want to find K and we know the half-life. So I'm going to rearrange this for K. So I'm going to multiply by K on both sides. That way my K's cancel out on the right. Then I'm going to divide by T half on both sides. That's going to cancel out my left. So I'm left with K is equal to 0.693 divided by the half-life. So we can put in our numbers there. 0.693 divided by the half-life, which is 50 from my graph. That ends up giving me a rate constant of 0.0139. So let's fill that in here. And our units for the rate constant, again, it's going to be different each time based on the order. However, all these questions are about first order reactions. So these questions in this skill will all have the same unit for rate constant. You can either find it by looking at the rate equation, or we can find it by looking at the equation we just used. So we used an equation, K equals 0.693 divided by T half. 0.693 is just a number. It doesn't have a unit, so that'll be 1, divided by T half, which is in seconds. So that's 1 over seconds per second. So our unit is going to be per second for the rate constant here. And that's going to be true for all the questions in this skill because they're all about first order reactions. Okay, lastly, we're asked to determine what the final concentration of Xl2 will be after the reaction has proceeded for 250 seconds. So we've got two methods to do this again. We can either draw it out like a table, or we can do it by calculating it. Let's do the calculating method first. So with the calculation method, we're going to take the time and we're going to divide it by the half-life. So that's going to be 250 divided by 50. That gets us 5. So 5 half-lives have passed. So that's the answer to our first question. The second question asks, what will the concentration be after 250 seconds? So it starts out on our graph at 16. That's our initial concentration. So we start out with 16. Now for every half-life that passes, we're going to multiply that by a half. So we're going to multiply it by a half 5 times for the 5 half-lives that pass. That's the same as multiplying by a half to the power of 5. So if we put that into our calculator, we're going to get out a concentration of 0.5 molar. Let's check that in our answer box. Awesome. So that's one method of doing it. We could also use the table method. So I'll show that to you now as well, in case you prefer that. So we've got the concentration of Xl2 and we've got time. So the initial concentration of Xl2 is 16 molar and the time to start with is 0. Then we know after one half-life have passed, so after 50 seconds, we know that our concentration will have halved. Half of 16 is 8. After another half-life have passed, we'll be at 100 seconds and 8 will have halved to give 4. After another half-life has passed, we'll be at 150 seconds and 4 will have halved to give 2. After another half-life, we'll be at 200 seconds, 2 will have halved to give 1, and then one final half-life will be at 250 seconds and 1 will have halved to give 0.5. So that also shows you we had 1, 2, 3, 4, 5 half-lives to get to 250 seconds. And our concentration halved 5 times to get to 0.5 by the end.